on our mission to Mars, we need to make sure that the passengers of the ship are well accommodated in terms of temperature in the cabin. So we are going to be implementing a temperature sensor to make sure that throughout the way from Earth to Mars, that the temperature within the cabin of the ship is suitable for passengers. We're going to do this by implementing a Arduino equipped with a temperature sensor and an LCD monitor to display the temperature in the cabin. This module will be placed in the cabin, and it will check the temperature at all times to make sure that it's suitable for the passengers, and it will notify the crew whether the temperature is safe, moderately safe, or unsafe, and it will also have a sound emitter to let the crew know, so they can immediately attend to the situation if the temperature is out of hand.
Hey Austin, what's that?
This is going to be our temperature sensor, the whole setup that we're doing for it. It's going to start with the Arduino, which is connected to an LCD screen. We're going to use this LCD screen to show a precise measurement of what the temperature inside the spacecraft is. We then have our temperature sensor down here, which is, well, as implied by the name, going to tell us the temperature. Above here, this little circle, that's going to be our speaker. It's going to make a beeping noise when the temperature gets too high or too low within the parameters that we've set. To power it, we will be using 3 9-volt batteries in parallel. We're doing this so that we can move it around the spaceship if needed, rather than building multiple, which will take a lot more resources and won't allow us to use as much resources when we get on the planet.
So what temperature are we going to display as like safe or not safe for the passengers?
I'm not certain. The body can't be too cold or too hot. I mean, too hot and we'll sweat, we'll lose water, which we need. Too cold and you'll burn energy too quickly and we'll lose food faster.
Yeah, both would be very bad for both us and the passengers. So let's start with the top temperature. What's the highest that the human body can handle before it starts to feel uncomfortable?
Probably 85, 90 degrees.
I mean,
I'd even say that 90 is a bit too hot.
I'm thinking 80.
Yeah.
I think 80 is like optimal.
like, I think that's like a good temperature for a passenger. We're also trying to keep our ride suitable and like comfortable too. So I think 80 is a good temperature.
Yeah. What do you think, Ryan?
Yeah, I agree.
Yeah.
Okay, what about low? We need a low. Like, what's the lowest it can go before it starts becoming like?
Obviously, it has to be above freezing, so anything
Yes, okay. So, I mean, I'm thinking like maybe like 60, 55. I'm thinking 55. I think like lower than 55 would be pretty bad. They're bright. I mean, I don't think we need to have the temperature like that in the first place. That we would need to accommodate them with jackets. We want to make it optimal so that they shouldn't have to wear like 3 layers. So we'll do 55. Now we should have a bit of error because, you know, if we were to utilize, say, a temperature sensor, there is going to be a certain extent where it does not need to immediately go off and notify the team because it's not a dire emergency situation. So what level of, like, what percent or like what amount of error in degrees should we use that would be like optimal?
I'd say about 2 or 3 degrees of error would be good.
Is it 2? So would that be like for potentially unsafe? Would that be like 80 to 82 would be good, and maybe 55 to 53? And that's like, okay, there might be a problem.
So no, I think we should raise the upper from 53 to 57, and that way we can keep it just a little bit warmer for the passengers.
Right, so are you proposing that we use 60 for the safe range?
Yeah.
Well, okay, so 60 for the safe range, so that means 58 for the, if we're doing a degree, like a 2 degree error. That makes sense, okay. So we'll do that, and of course, clearly anything below 58 or above 82 is a concern, and the team will be immediately notified. That's what we'll do. All right.
Sounds good. What do you think?
This is our temperature sensor. It uses this sensor right here and the batteries to supply power and check what temperature the air is through an analog signal. Then the Arduino, if it is outside of the safe zone, like if it is too hot or too cold, then it will play a sound on this through the Arduino. It has batteries right here, so that just in case power goes out, or if we need to move it around, power is still supplied, so that we can tell whether it is too hot or too cold.
And this will be able to notify the team?
Yes, this would be able to notify the team in case anything goes wrong, and make sure that we can get the temperatures back to
normal levels?
Normal.
Okay, that makes sense.
So this is the Arduino board. and we run the code through it, and it provides power to the breadboard, which we use to organize the code run through the Arduino and its processes. And then what the information we input into the Arduino board runs through the program that you made and goes onto the LCD screen and displays our output.
As you can see here, we have multiple parts that are important to the function. Most importantly, we have the battery, which we've hooked up in parallel to make sure that in case any one of them falls, we'll still have some backup. So make sure we have the ruggedness required to survive on the Martian topsoil. As you can see here, we have an which is able to convert electrical impulses into sounds that are hearable, audible to the human ear. The temperature sensor is able to detect the ambient temperature from its surroundings and convert that into a voltage that we can read and convert it to a human readable format such as Celsius or Fahrenheit.
Oh, that's very cool. You don't have this. Yeah. Austin, you have the
design, right?
Yeah, man.
I'll see you see what. I gotta do the
wallet. Let them get close.
Hey Tyler, what is that?
So I'm working on the code right now, and basically, let me just run it down for you. So we have our two dynamic variables here that are changing throughout the execution. We have our variables that we predefine, so they don't change at all, right? That includes our limits, and then that also includes the piezo pin, as well as the number. Next, we're gonna set up our variables, right? Like initialize all that. The LCD screen, the serial or console terminal, whatever you want to call it, as well as our pins, A0 and A02, right? Set the input and then output. Next, this is the function that's like continuously like playing on loop, right? We have, so basically, it gets the analog output, I guess, from the temperature sensor, and then converts that to Fahrenheit because to like get the temperature, you know. And then we display that on the LCD screen, play the audio if needed, and then we also printed it in like the console to make sure that it's like all working and stuff. And then we set the previous Fahrenheit to the current Fahrenheit, and then I'll just delay for a little bit so that's not continuously playing. Next, we analyze, like this is functions used in the display LCD and the audio. This basically just like returns a value based on if it's above or below the limit. And then for the display audio, LCD, it just displays the LCD, like the data on the LCD if it needs to, pretty much. And then finally control audio, that displays the audio above or below the limits that we established.
Hey Tyler, tell me about the schematics.
Alright, so I actually have it right here. So we have our batteries right here connected to the Arduino's ground, and then the batteries go into the bin of the Arduino to charge it when, like, you know, it's actually implemented, right? Next, we have the 5-volt pin of the Arduino, and this goes into the LCD and the temperature sensor, right? And then in our temperature sensor, along with the ground pin, we have our Vout, which sends the signal to the analog pin that tells the Arduino what the raw analog of the temperature is, right? Next, we have our D2 pin. This basically powers the piezo, which like plays the sound, right? And then we also have our SCL and our SDA for the like actual LCD screen, right? And then, yeah, I think that's pretty much it.
Whoa, what is that, Tyler?
So, I don't really know. It's kind of just spitting out random characters here on the LCD screen. When I change it, it changes the characters. So, be like that, for example. You know, that's kind of weird. Apparently, the issue we were having is that right here, we were actually trying to like concatenate or whatever an integer with a string or character list, I guess, and it didn't really like that. So what we had to do is that we have to like print the like Fahrenheit first, like the actual number, and then the string at the end. So, but yeah, we'll get working on that.
What are you doing over here, Tyler?
So I'm trying to figure out a problem right now with the like temperature sensor. And what happened is that, so right now it's supposed to be outputting like a big value right here, but whenever I change it, it's a huge like value. It's supposed to be small. So we didn't know what was up with that. But apparently, in the analog port, A5 and A4 are just broken. Because if I change it to A4 or A2, we'll do A2 with the temperature sensor. And then, but when I change it, it goes back down to like an actual value, which is weird. So I couldn't really find anything about this online, but yeah, now we know what happened. All right, what you working on here, bud?
Well, we currently have a problem.
What's the problem?
There's no sound coming out of this because this is at such a high value with the gigawatts, and we haven't set it to ohms yet. So we just need to fix that so we can get this thing up and running. You know.
Let's see it. Oh yeah, there we go. So now it's working.
Oh yeah. Hey Tyler, what did you learn?
So I learned how we can use the temperature sensor and get the output the raw data from it, and then convert it to Celsius and Fahrenheit for us to use for other purposes. All right, Austin, what did you learn?
Hey Tyler, I learned that putting our 9-volt batteries in parallel will allow them to last longer on the space journey.
Roman, what did you learn?
I learned that the higher the resistance is, the lower the sound of the piezo.
All right, so Dennis, what did you learn?
I learned that the Arduino processes code in a very specific way and transfers it to the breadboard, which organizes, right, and then sends it to the LCD as R code output.
Go. So what did you learn?
While adjusting our Arduino sensors, I learned about the different temperatures that are best suitable for human inhabitants so that we could accommodate our passengers the best way as possible.
All right, nice. All right, Charles, so what did you learn?
I learned that there are multiple types of thermal sensors, not necessarily ones that deal with only resistance. There are also some that deal with voltage as well.
Go. All right, Carson, what did you learn?
I learned how the temperature control module on an Arduino can measure the temperature as an analog signal and then return it as a number on the LCD screen.
We gon' rock this club, we gon' go